Okay, can anybody hear me?
Yes.
Oh,
Yes,
very
indeed.
good. That's a good sign. Okay, we have about half our normal contingent logged on. We'll wait a few minutes here. We're still a little early.
Hey, Howard.
Yeah.
So when I do my presentation, I'm going to use my phone as a remote camera, so I will log in from it also at that point.
Oh, okay. That should work.
So just to let you know.
All right. Thanks a lot, David. Yeah, it's good to see you. You've been in the dark the last few times.
Yeah, you know, I was, I have to admit, I was laying in bed with my Chromebook watching, and I didn't want to give people the wrong idea. So.
Okay. Well, the cat's out of the bag now.
Yeah, I'm down in the kiln room today. You'll get a tour of the mess. So.
Okay, looking forward to it. That'll be awesome. Yeah, we're gonna have we have a good lineup tonight again, of course.
Lisa.
Howard, everybody. Good evening.
So I'm thinking about playing with epoxy mirrors here once the cold weather sets in.
That's a good idea.
Did you ever do anything with either one of those bases I sent you, or are they just on a shelf?
Yeah, they're on the shelf because I have to have a lip around them in order to hold the epoxy. And I was doing other things, so I never did anything with them, but they're on the shelf.
Okay, I was going to say, you want to stand one back?
I can do that if you would like for me to, sure.
And I'll put it in my kiln. I have to build the air bearing first.
Yeah.
But yeah, I'm going to try and spin one up. So.
Okay.
Thank you.
I'll email you and get your address. I don't remember your address, so I'll just send you an email and you can send me your address.
That works.
Get it shipped out. Yep, no problem.
Thank you.
Sure.
Okay, hi Lisa. Lisa, can you hear me?
I can hear you.
Okay, very good. All right, how are you doing today?
I'm doing well, thanks.
Good. I think I'm not the only one who's excited to find out what you've been up to.
We've been up to a little bit, so we're making slow progress.
Okay, well
that's better than none.
That's better than none. That's absolutely right. Yes, indeed. Okay, we're slowly getting up to our normal participation here. Yeah. Okay, I think probably a couple more minutes and we'll have a quorum and we'll get started. Let's see who all's in here. Yeah. Okay. Okay. All right, well, there's Greg. Hi, Greg.
Hi there. How are you doing, Howard?
Doing really good. I think
Hi, Lisa.
Greg, how's it going?
Good.
We just about have our normal sized group. We'll give another minute or two. For people, I do know that a few people aren't available to join us tonight live, and they'll just catch the recording. Has anyone tried to view the recordings yet, by the way?
Yeah, I viewed the one for Thursday night because I couldn't make it, and it was perfect. I had no issues with it.
Excellent.
Yes, and I did too.
Okay, that's good to hear.
Yeah, worked fine.
Yeah, I know I had a small problem when I posted the link on cloudy nights. the link didn't work the first attempt. And I really
After that,
don't
it
know
worked
why.
perfectly.
Because it just, yeah, the second attempt worked, but why the first one didn't? Because it was just copy and paste.
Howard, I wanted to mention, since the subscription for the cloud storage is monthly and it's pretty steep, I think we would want to relocate these to something free like YouTube eventually.
Yeah.
So I think I didn't realize that you would post the link publicly, but if we can later go and update those links to replace them with YouTube links, that would be perfect.
Sure. Does anyone know how to do that?
I mean, in principle, I think it is as simple as someone downloads the video and re-uploads to YouTube, or there might be an easier way. But yeah, if someone knows how to do it more easily, then I'll be all ears.
Yeah, me too. Yeah, because having it on YouTube would be great.
Cloudy Nights now has a limit. You can only go edit your posting for like 48 hours or 24 hours.
Oh.
So you might have to delete it or just do an update. So,
Okay.
you know.
If we get it on YouTube, we'll just post an update that's been done.
Yeah.
Okay.
Okay. So, all right, I think we're ready to start here. So this is day 3 or session 3 of the 2020 ALTAS workshop, and the agenda for today, we have 4 presentations. We're going to start with Lisa Brodhacker's update on her spin cast epoxy mirrors, research that she's been doing for several years, quite a few, more than several years now. It'll be followed by Zane Landers talking about his 14.7-inch f2.89 Dobsonian. We'll have a very short break in between that and Tong Liu's talk about his UL 40-inch f3.3 telescope. And then we'll round out the evening with David Davis talking about resizing Pyrex blanks in his kiln. So given that I have nothing I could say that will add anything of value to this right now, I'll just say take it away, Lisa, and we'll get started.
All right. Well, let me see if I can get this up. This says the host disabled participant screen sharing.
No, let me check here my settings. One participant, share at a time. Okay, try it now.
Yeah, that works.
Okay.
All right, do y'all see that?
Yes, we also see your slide. Oh, there you go. Now it's full screen.
Okay. All right, good. All right. Well, it's really actually been fun to see you guys again. It's been several years since I've been to Oregon. So I'm always enjoy seeing you guys and the real mirror makers out there. So I work at a small rural university. It's an undergraduate university. I'm a chemist. And so you'll see that my students are extremely important to me. And really, they do a lot of the work here. And so I have to really give a good shout out. And I'll do that again at the end of the presentation. But it's a lot of fun working with these students. I did put a picture of Roger Angel in here, and I have no interest in making very large mirrors like this, but you know, he wasn't the first one to use the spin casting technique, but he has perfected a lot of the engineering aspects, and we have used a lot of that information in our spin cast mirrors as well. But as you can see, it takes a long time to make a large mirror. And we believe, if we can perfect these epoxy mirrors, they do have the potential to be very big. And we can make a mirror in about a month. It doesn't really matter how big it is. And of course, we can do it with a lot cheaper and a lot lighter as well, the glass mirrors. We have a lot to overcome, though, as you'll soon see. But that's okay. We're making some progress. We can make mirrors up to 2 meters, and I'm going to show you the equipment a little bit more. We haven't made a 2-meter mirror yet. The largest was this one. It's a 1-meter mirror. And I'm going to tell you about this, what happened to this mirror in a little bit. And I have to give Peter Chen credit for this comparison that I'm going to give you here. And he, of course, is working with NASA Goddard, and he's doing epoxy mirrors as well. And he's definitely made a lot more progress than I have. I think he's got a lot more resources at his fingertips. But he made this comparison, and I think it's a good one. And I'm not going to go into the history of telescope mirrors because you all know more about that than I do. But as you know, as telescopes became bigger, the mirrors had to become a lot thicker. It was kind of like a sumo wrestler, right? If you're going to be a sumo wrestler, you want to be a big guy. I would hate to be the little guy here. And that's the same thing with these mirrors. Here's the Russian BTA telescope mirror. And, it was only 6 meters in diameter, but it weighed 42 tons. And that's because it had to be really, really thick. We get to the 1980s, and then many of the large telescopes are using thinner mirrors. And so they're more like ballerinas. And we want that emphasis to be on flexibility. We want to be able to move the mirror faster and easily and so forth. And a good example of this is the Subaru telescope up on Mauna Kea, where now it's only 20 centimeters thick, and you can see all of the actuators on there as well. And so we've gone to an 8.2 meter mirror, but it weighs half of what the 6-meter mirror weighed. Our mirrors are more like Tinkerbell, okay? So yeah, we still want the flexibility, but we're gonna add a little bit of chemical magic to them, and we're gonna improve our mirrors and make them smart telescope mirrors. And I'm gonna actually tell you about several of these, how we're adding multi-walled carbon nanotubes, the polyhedral oligomerical sesquioxanes. I always tell my students when they're doing a presentation on those POS compounds, I say, you always have to say the compound at least once in your presentation. Then after that, you can say POS. And so from now on, those are going to be named POS. But the reason why we're doing this is we want to get, improved physical and chemical properties of our mirrors, like reinforcing the mirrors with the nanotubes. We want to get more heat and chemical resistance and so forth. And I'm going to tell you about several of these as we go along here. And if we look back in the literature, we see that about every 10 years, somebody tries to make a polymer mirror. It dates back to the 1950s where they were making replica mirrors. And then in the 1960s, you get, I think it was out of Caltech, you have Layton's 62-inch, and he actually made a spin cast epoxy mirror that he used for infrared. Later in the 1980s, somebody made some off-axis mirrors, again, using them in infrared. But it wasn't until about the 2000s, around the year 2000, that chemists actually started playing with these epoxy mirrors. And the first ones were out of the University of Iowa, and they were just making really small mirrors for infrared spectroscopy. And then in 2004, at USC, the real USC in South Carolina, we were working with these mirrors, and we got what we believe is the first astronomical image captured with an epoxy mirror. And then in 2009, because my advisor went back to industry, he gave up the project. And so he asked me if I wanted it, and it was a no-brainer. And so that's when the project came to Lander University. Now, while I was in graduate school, we did a lot of experimentation on different compounds. What exactly do we want to use for the mirrors and such? And we ended up using these compounds, and they probably don't mean anything to you, but they mean an awful lot to us. So up here in the upper left-hand corner, we've got the bisphenol A epoxy, and those epoxy rings do open up to give us a little bit of an expansion, which kind of negates a little bit of the shrinkage that we get in the epoxies. Not a lot, but a little bit. And those benzene rings are very important to stiffen our polymer. Then we've got the amine over here on the right. Notice those NH2 groups are flanked by those other ethyl groups. They look like little arms there. And that's actually going to allow us to slow the reaction down. We want the reaction to go slow because a lot of things have to happen before the gel point of the polymer. Once you get to that gel point, that's the point of no return pretty much, that's when things start getting situated pretty tightly there. And so we want to be able to degas the materials. We want to be able to pour it. We want that spinning parabola to stabilize all before that gel point. And then the other epoxy here on the bottom is a diluent that we use just to lower the viscosity to help it spin out a little bit easier here. So this is just a schematic of our equipment. Notice on the bottom here, we have the 3 concrete columns, and those hold the triangular support frame, which holds the air bearing. And then of course the air bearing is connected to a stepper motor, which turns the steel plate. And then of course that's holding the epoxy. And back in 2009, we were putting this together. So these are actual pictures here. You can see the 3 columns. They've got the feet on them that we can manipulate to make sure everything is level. And then we've got the triangular support frame holding the bearing there in the middle. And then these 2 guys from USC, the machine shop, came up and helped me put everything together, which was really nice of them. So you can see the platter in the middle, that's 1 meter in diameter. And then we put these arms on the platter so that we could spin up to 2 meters in this oven. And then here we're putting the oven together. So everything from the platter up is housed in the oven. And we're using these heat rings on, we have a hexagonal oven. And so we have 6 of these heat rings inside the oven. We did a couple variations, but that's what we currently have today, is the 6 on 3 different sides of the oven there. And then we just added these little feet just to help so that it wouldn't bend down on the edges there. And then we were having problems getting the temperature that we needed in the oven. And so I think it was 2012 or so, I found a really good heat protectant that's used for the food industry. And we used that because we didn't want it to flake off into the epoxy. So we took the oven apart, we sprayed all of these, and then we insulated everything on the bottom. You see the blue insulation, that's a formaldehyde insulation, and so now we're getting the temperatures that we need, and that worked out really, really well for us. So when I was at USC, my advisor's idea was to spin these mirrors in a Rubbermaid container. You can just buy the Rubbermaid container off the shelf. I think the largest mirror that we made was probably 10 inches or so. And another idea he had was to use progressively thinner layers as you went up in the mirror, and which is a very good idea. We still do that today. We also tried to use glass microspheres just to reinforce the mirror, because the Rubbermaid containers would just allow us to pop those mirrors right out, and then you would just have the mirror by itself. But one of the biggest problems with this is that the outside, because the Rubbermaid container is flat, the outside of the mirror was thicker than the inside, than the middle. And as I was reading literature, a lot of the literature back then, it kept coming back to that epoxy being uniformly thick. And so when I got the project here, that was one of the first things I wanted to look into, see if the uniform thickness actually makes a difference. And so because the epoxy is a liquid, we have to have something to hold the epoxy. And so we decided to try making a mold that would become part of the final mirror. And one of the first things that we did was we tried a polyurethane foam just to keep it lightweight. And we had it machined, got a little lightweighting pattern on the back here. And then on the picture on the right, what we did is we had it machined so that the curvature of the top of that mold matched fairly closely to our spinning parabola. And then we went ahead and we spun some epoxy, and it's got a little dimple in it, but it looked actually pretty good. And I sent these up to Bruce up in Pennsylvania. He's been really nice to do a lot of testing for us. He had to do some creative testing because, I mean, this was a new thing and we weren't anywhere near where we needed to be. But one of the first things he noticed was the image coming off of that mirror looked almost like the lightweighting pattern on the back, which told us there were some areas that were roughly parabolic, but we had a major problem because that foam just wasn't stiff enough. And so we decided to go to the other end of the spectrum And we took an aluminum mold and we did the same thing. We did a lightweighting pattern on the back, and then we machined the top surface to roughly match, what the spinning parabola would be. Now it looks like the epoxy, which is the yellow portion here, it looks like it's all scuffed up, but that's actually the aluminum mold here. And this actually worked really well. What we did is we took I'll tell you about the test that we did here. We took a flashlight. The flashlight had 5 LEDs in it. And we situated that down the hallway of maybe 50, 75 feet. And all we did was we shined the light on the mirror, and then we took a picture of the image that was coming off of that mirror. And so I wanted to try the ones that we made in graduate school. And so the Rubbermaid containers, that image looked really rough. We did take that polyurethane foam mold, and we tried it one more time by putting an aluminum honeycomb backer on it just to see if it would stiffen it up, but that didn't work either. You can see there's a lot of problems with that too. But our aluminum mold, we were actually really excited because we were now resolving those 5 LEDs of that flashlight, and that told us that we were onto something. And so we took a big step. Not the best idea from an engineering aspect. I'm not an engineer. And we went ahead and we spun that. We did the same thing with a 1 meter mold, an aluminum mold. But I didn't think about the mismatch of CTEs of the aluminum and the epoxy. And so I did ship this one up to Bruce as well to do some testing on it. That was in November. And apparently it gets kind of chilly in Pennsylvania in November. And he left it in the crate outside. And then when he took it into the lab and he opened it up, and this is what he saw, that epoxy had cracked. It was a lesson, that we had to learn. But so we had to go back and work on that CTE problem. One of the things we decided to do was, why not just make the entire mirror out of epoxy? That makes perfect sense. But the epoxy is very soft. And so I had a student investigate these multi-walled carbon nanotubes. And we tried 2 different things. We tried an unfunctionalized nanotube and a functionalized. And the functionalized nanotubes just have a functionalized group on them that now they will become covalently bonded to our polymer. And so these are TEM images. This one is the unfunctionalized, and you can see that we did not have good dispersion of the nanoparticles at all. Again, we were very excited when we saw this, because with those functionalized nanoparticles, we got a really good dispersion throughout the polymer, and that was really important because you want to have as uniform CTE as possible. And so Drew in sunny Florida, we don't hear much from him these days, but he helped me out with his 3D printer, and he made like an inverse mold. You can see the bottom left here. We had 2 halves, and this one was just a 4-inch. We wanted to start small, see if this was going to work or not. And so we took that mold and we put it together, and we poured in some silicone rubber. And you can see the silicone rubber at the top right. It still has some bubbles in it. We needed to degas that a little bit longer. But once that cured overnight, now we have a rubber mold that we can pour epoxy in, and the mold will not be part of the final mirror. We can just pop the epoxy right out of that. And that worked really well. And so what he did, I don't know, can y'all see this? Can y'all see this right here? Or do I need to make it larger?
I can see it, but I don't know if anyone else can.
Yeah, I can see it too.
I see it.
Double click on her video, like on her image right now, it'll become the main screen and you can see it larger.
I don't know how to do that.
Up in the right-hand corner, there's a little rectangle with a smaller rectangle. You
Yeah.
click that, it'll switch it. So when I click it, I see you full size and the display small size.
Yeah, I don't know how to do that. We all have to be brave for right now. I'll show it to you again if you're interested. But he went ahead and made 6 of these. So it made like a little pie. And we've got a lightweighting pattern in the back. And then we took that and we poured silicone rubber in it. And so you can see that this is now ready to hold epoxy. And so on the next slide here, what we did is we took this mold and we just filled it with epoxy and cured it as a flat. And then over here on the right, we now have, let me change this because y'all are in my way. That's okay. Whoops, wrong one. And we went ahead and machined that to have, again, the curvature on the top of it with a lip around it. And then we took that and we spun just a really thin layer of epoxy. And that's this mirror here that I'm holding here. And it's black because of the carbon nanotubes. And it doesn't have a reflective coating on it either. And this mirror, 10 inches, it performs just like the aluminum mold did. So it resolves those 5 LEDs in the flashlight. And so that's a really good thing. We're making some good progress there, but we still had to figure out the whole idea for, let me see if I can get, there we go. The whole idea of the CTE. We had to fix that. And that CTE is still haunting me. And one of the things we did is we took these POS compounds, and the POS compounds are actually really well known for lowering CTE. And we've got the POS cage right in the middle where it's got the silicon and the oxygen. And that's the part that actually torques inward. So it kind of gives you a negative CTE because of the silicon oxygen bonds. And these POS compounds, you can functionalize them like we see here with 8 functionalizations, or you can do a monofunctionalization. And so one summer, one of my students, she did, you can see on the x-axis here, she did a 1 POS, and we did keep the carbon nanotubes in there. So she did a 1% carbon nanotube and a 3%, and then she also did the 8 POS to see what it would do. And then she did various percentages of the POS. But you can see that the CTE, the y-axis here is CTE. The CTE is still really high. We're still 60, 70, 80 parts per million. And so the POS wasn't working for us. And we think we just got too many steric effects. If you got too much stuff in there, it's not going to allow the reaction to go forward. And I think that that's what probably happened with ours. So it didn't look like this was going to work. We did take some, well, let me show you this first and then I'll come back to that. So my current student, he's from Zimbabwe. His name is Learn More, actually. Interesting name. And his brother's name is Try More. So I think that's really interesting what they name their children. But he synthesized this compound right here in the middle on the bottom. And here's the picture of our epoxy that we're currently using. So this epoxy mimics ours, just has the green arms on it. But it's the silicon oxygen bonds that we need that's going to give us that torquing inward and hopefully a lower CTE. COVID kind of stopped us in our tracks there. So we're still in the middle of testing these, but it looks like they're kind of doing the same thing POS is doing. So it doesn't look like this is going to work. There are compounds, inorganic compounds that have high negative CTEs. We did use zirconium tungstate one summer, but the problem with that is it's so dense that it just kind of filters out of the epoxy. But we were curious, and so we just kind of stuffed a sample of epoxy full of that stuff just to see if it's going to lower the CTE. We got down to 8 parts per million, which, you know, now we're in the realm of soda lime glass. So the negative CTE inorganics may work. We just have to figure out how to get them into nanoparticles, which I think would be better suspended in the epoxy. And so we're looking into that as well. So the CTE problem is still a problem. And I'm very open to suggestions if you have any. The last thing I'll say about the mirrors is we are looking into putting a magnetic component into our mirrors, because we have the advantage that these mirrors, when you heat them up to the glass transition temperature, they'll become rubbery. And it is possible that we can heat them up, apply a magnetic field, move the mirror, manipulate the mirror, and then cool it down. And that final shape, we can just obtain that final shape. And so another one of my students worked on functionalizing the nanoparticles because we seem to get better dispersion that way. And again, we made some really small 4-inch flats that we sent to Bruce. And he said, even at room temperature, he can manipulate the epoxy with the magnet and move it several waves. So I think this holds a lot of potential as well with our mirrors. So we're still looking into those. And we're also looking into, we used iron oxide and we looked at cobalt and nickel, but we're now looking into the lanthanides like neodymium, which are, you know, is a very strong magnet, and gadolinium, so that we wouldn't have to have a lot of nanoparticles in there, and we could still get the magnetism that we wanted. Again, I have to shout out to my students. They're really amazing. I do have the advantage of having these students in their sophomore year in my organic class, and I get to pick the overachievers, and it has really proven to work really well when they're doing research. And I have several that have gone on and got PhDs. This young lady in the top left, the one that's standing in the front, her name is Brenda. She just finished her PhD this past March and is now at the Duke Human Vaccine Institute working on a COVID vaccine. So I'm really proud of her. But it's really fun to kind of jumpstart their careers, giving them this experience, and the funding sources have really been just a real blessing for that as well. So I just really have to thank my students a lot for all the work that they have done. So that's all I have. So I'm willing to, if you have questions or if you have suggestions, I'm all ears.
So just to make sure I understood what you were saying a moment ago, Lisa. So you have a magnetic component in the epoxy with the intention of being able to actively change the optical curve or flatness of the surface.
That's correct.
Right?
That's
okay.
correct. Yeah, that's what we're doing.
That's our super cool.
Yeah, it is really, and what was really exciting too was when Bruce was moving it around. Now we have not spun a mirror yet. He has just worked with some flats just to see if it was going to work. And he was pretty excited just to see, even at room temperature, you don't even have to do the whole heating of the mirror or anything. So, and if we have different types of magnetic particles in there, I think it does have a lot of potential.
And you said he could change the surface by how many waves?
I don't remember the exact amount, but he said several waves. I have it in one of my optical testing. He sends good reports, and so I wish he was here. He could give a report for that, but yeah, I think it holds a lot of promise.
Okay, and I have a question from Rob. He wrote it on the chat function. He's asking, do you think you could spin a layer that is on the order of 10 to 50 microns thick?
Of epoxy, I'm not quite sure that we could spin it that thin. I think we've gone down to 2 millimeters, and that's just because of the spinning. When you have a small amount of epoxy, trying to spin that out in a certain amount of time, we haven't been able to do anything that thin. Yeah, that thin of a layer.
Now, do I understand that you're not doing any polishing after you spin?
We are not. We have had people that have tried polishing, but the epoxy is really soft. So I have not done any polishing at all. The test results that I gave you are just spinning and then testing them. I think the last time I was in Oregon, we did some ronchograms, and I remember seeing Mel cringe looking at those ronchograms because they were pretty bad. So yeah, we've made some pretty good improvements, but we've got a little bit of ways to go.
This is Greg. I think I was one of the people that did the Ronchi.
Oh, I remember that.
Yeah, and actually they weren't that bad, considering what maybe we expected. And the surface actually was pretty decent. And that's always been one of the the questions about using epoxy is what do you do with the surface? But your tests are, at least what I saw a couple of years ago, was pretty interesting, and just being able to use the spun surface. And then I've been fiddling around with adaptive optics, not active. That's really exciting. Being able to tweak the mirror with comparatively simple supports and stuff would be really really interesting. So really cool.
How like good or bad would you say they were? Like, would you say they would hold up to something like close to diffraction limited, or much worse than that? Like what, like whatever the RMS is for like a 1/4 wave PV mirror. I'm not great at my testing.
You know, the ones we saw were the last time she was up, and I think that was what, 2 years ago or 3 years ago. It's been a while. Would I trade it for any of my mirrors that I have in my scopes? Well, no.
You trade it for like a
not
cheapo,
close,
like mass manufactured mirror?
No, I doubt it. But if you were going to do something in the infrared, I think it would probably already work.
I think so too.
You know, you might have to go down to 8 micron or something. But I think you'd get a decent image. So it's more that way. It's more living within the results you get.
Yeah.
But as far as what we would, we would probably call it a 3 or 4 wave, 5 wave, 6 wave, something like that.
Is just the roughness or the inaccuracy, the parabola, or both?
Probably more the inaccuracy of the parabola at the time.
You could, if it was not like a really weird curve, if it was just like overall like poor correction, you could conceivably, work around that.
Well, that's why the adaptive portion is so interesting, being able to bring it back in.
Or
and
even you could make a Schmidt corrector or something, or a sub-aperture corrector of some kind, I guess, too.
But the adaptive stuff is well understood how to do that. So that technology exists. So getting a substrate that you can bend with just a magnet.
The magnet. That's
cool.
just so hard to picture. My mind just thinks of like the ferrofluid stuff, but the idea that you can pull on the mirror, with a magnet and replace all of that, of the stuff that goes in these active or adaptive optic systems with just magnets is pretty mind blowing. And you could vary them to just like an active optic setup too. That is amazing.
Yeah,
without any mechanical stuff, just like electromagnets in a support system.
Right, just an array of magnets and something to hold
or anything.
Yeah, that's very exciting. So cool. Sorry.
So Lisa, I have another question on the chat from TLH. They're asking, have you done any scatterometry on the finished surface?
I have not. I don't know what that is. I told you I'm a chemist, unfortunately.
Okay. Well, I think you'll know the answer to this next question. What RPM do you spin your mirrors at?
Well, I mean, you can change the focal length by just changing the RPM. So I think we spin these for an F4, which I think they were spun around 15 to 20 RPM. So it wasn't very fast. They're fairly slow, but
okay.
I did try a fast mirror once, and the epoxy flung out. So that wasn't the great thing to do.
Now with the RPM, if I wanted to make a 1 meter F4 versus a 20-inch F4, it's the same RPM for whatever focal ratio. It doesn't matter how the size. You have to bring up the RPM up or down for a larger mirror of the same focal ratio.
Well, you might want to bring the RPM up just a bit, just to get the polymer to spin out a little bit faster, and then slow it down before it starts to cure. We have done that with that with that 1 meter mirror. We did do that.
Okay. And now you have had a few mirrors coated with aluminum, I think, and also you tried a silver coating or two.
We did.
How did the aluminizing work? Because I know that most coating companies that use aluminum don't want a substrate that has any outgassing.
Yeah, there's no outgassing on these because everything in the epoxy is reactive. So we don't have any solvents that are going to, going to gas out or anything like that. Drew down in Florida has coated several of my mirrors, and he doesn't have a problem putting them in his big coater.
Okay, well, that's cool.
Yeah.
And the silvering didn't have a problem either.
No, I mean the silver worked okay. It didn't seem to adhere as nicely as the aluminum. Because you could do a simple tape test where just take a piece of tape and put it on the silver, and it did pull off a little bit. But the aluminum did do a lot better, and I still have a mirror from 20 years ago in graduate school that's aluminum surface still looks really good. So I think the aluminum is the way to go with this. I was interested in the spray silvering that somebody was using. Was that Rob that was talking about the Midas?
Rob talked about it, yes.
Yeah. I was curious if that might work on epoxy, so I might look into that.
Yeah, the angel gilding provides you with a sensitizer for plastic substrates. And I think that it may help the adhesion. I think it's intended to help the adhesion, or at least get the reaction to go, where on glass it's, something else. So of course the durability isn't going to be the same as aluminum. But when you're talking about cheap optics and, cheap coatings and a way to protect them, then I think, what you're doing may be a path forward to a low cost mass production kind of way to make some big parabolas, depending on what the application is. You may be already there if it's long wave infrared, but there's lots of potential here. Very good, thanks.
Yeah, I have had Raytheon contacted me. They wanted to use the mirror for a non-lethal laser system of some sort. I can't remember what it was, defense system or something like that. But we weren't quite ready to deal with Raytheon.
They own me now. That's what I work for.
Oh, nice. Who is that? Is that Rob? Okay.
Yeah, it's Rob. Yeah. We work for head-up display outfit of theirs now. Yeah. Oh my. Interesting. Well, I'll see if I ever run across some non-lethal laser people in my new employer. Yeah.
Can I ask
That's interesting.
Somewhat orthogonal question, because I first came across what you were doing because I was looking at it not so much from the spin casting of a finished mirror, but I was looking for ways of spin casting a form that I could make a refractory mold out of that can go into a kiln to allow me to slump the meniscus. So so I guess my question is, does this require these exotic epoxies, or can some pedestrian epoxy be used to create something that is not intended to be the finished product, because the epoxy that's being cured is merely a mold for something else that's going to then be hand polished and figured and all of that stuff. So it doesn't have to be super precise. So I'm wondering if this technique would work with just, epoxy that I could get, at a big box store, or automotive supply or whatever, does it have to be these exotic chemicals?
Well, when you say kiln, I hear high temperatures.
Yeah. So the epoxy wouldn't go into the kiln.
Oh, okay.
So I need to make something out of a refractory material that's going to be going into the kiln, but that has to be cast against something. And so if the epoxy were the thing that I would cast the refractory material against, then I would have, you know, the shape that I wanted to go into the kiln that I could then put the glass on to slump the glass.
Yeah, I don't see why not. I mean, people have used epoxy for other types of replica type mirrors. So I think it's possible. But
It
I
would
mean,
be it would be not unlike your silicone rubber mold or the mold that Andrew sent you to create your silicone mold out of. It would have a curve to it, and he would probably put a dam around it and then put his medium in it. And when his medium had cured, he would remove that epoxy from it. So he would work just with his medium.
And what is the medium?
I don't know what he's using exactly. When I do it, I use a rapid set grout and vermiculite.
David,
and,
would the silicon mold idea be better?
Both have real merit. Can you spin the silicone?
The silicone's pretty thick. I don't know that you could get much spin. Plus, it cures a lot faster than our epoxy does.
Okay.
I mean, there's probably ways that you can add something to it to lower the viscosity. I don't know what that would be, but I wouldn't be surprised if there's something out there that would do that.
Think of it as a lightweight concrete will lay in against it. And as it hardens, then you'd lift that lightweight concrete off of the epoxy.
You know, you can 3D print flexible materials, and you could print your mold and use that rather than spinning it.
We're looking at like 1 to 2 meters, and I haven't got any 3D printer that will do that.
I do it in sections. My printer is 20 inches. So
yeah.
Just calculate out the sections and put them together and use that for a mold.
But even
interesting idea.
20-inch printer, though, that's pretty big as well. Like, I think, you know, for your hobby printers, you know, the one that I just got, you know, the Prusa, you know, it's got a 9x9 area, 9x9-inch area. So, so I guess technically I could maybe make something as big as 18.
Well, I got the 20-inch because I was interested in or not 3D printing spherical molds for my tools. I make my grinding tools using hex bolts with the head down and pour dental stone or hydrostone around them. And so I wanted to make molds for doing that so I could start with the radius of curvature that I wanted to start with, rather than trying to use glass to grind to get to the curve that I wanted.
All right, so we have one more question from chat. This is from Mel. Lisa, he asked if you could speak to surface tension and other issues that might affect laser figuring where the epoxy is vaporized in a controlled manner.
I'm not really quite sure what that means.
Mel, are you out there? Can you turn on your microphone and maybe explain more detail? I can guess.
Sure, this is Mel.
Here he goes, okay.
The idea then is to spot a laser on the epoxy and burn off that micron nanometer level amounts. So you would slowly sweep it back and forth.
Yeah, hey, you're coming in and out. I'm sorry, I'm not hearing
you. Yeah, I'm
you.
not hearing you either very well.
Okay, let me try this. Can you hear me better?
That's better.
Much better.
Okay. So the idea is to use a laser to burn off the epoxy in a controlled manner, maybe down to the nanometer level by sweeping the laser very slowly, controlling the intensity or the speed, so that you could reform the surface after it's cured. And I was very curious about surface issues and how epoxy vaporizes.
That's very interesting. I don't think I can answer that question, but that is actually something that I would actually be interested in looking into, because that's interesting. But I don't know the answer to that question.
A few years ago,
Another similar technique might be plasma etching, and I think they actually did that to the Keck mirrors. They polished them first to a very good, off-axis shape, and then they went in and did some ion milling, which is basically an ion beam ablating the glass to get super accuracy. You're talking about removing molecules at a time, of course, so maybe not 10 waves of correction, but epoxy might behave differently. So there's ways to get there, maybe. I like the idea, though. Boy, you could just put this in a spinning oven and pop it out, and it's done. I think that's what you should be focusing on.
Yeah.
Yeah.
I was curious from all of your perspectives how critical that CTE is. I mean, do I need to go ahead and keep pursuing that, or what if we made the whole thing out of epoxy, but it still has a high CTE? Is a high CTE a problem for astronomers?
It is, especially on cold nights in Minnesota or wherever Ed lives. I asked earlier about the 10 to 50 microns. If you can make your polymer thin enough, it is soft, and as you get a high delta T and things start shrinking and expanding, a very thin polymer has a much higher probability of not cracking. Now, I don't know what the specs are going to be for your polymer, but I've been through some similar stuff where we had an epoxy bond between two identical pieces of glass that was cracking, and we were able to solve that problem by making that bond as thin as we possibly could. So, and we took it down to like minus 40 C, I think, and no cracking. So that's why I asked that question. If you can get in the tens of micron range, maybe that might work. It's something to look at, but you'd have to figure out how to get a layer, that's incredibly thin.
Yeah.
Thinning.
Yeah.
So this is Mel. If I could put a plug in for high CTE mirrors, people
We can't hear you again, Mel.
any better this way?
Yes.
My gosh, 3 inches makes a difference. So I'll put in a plug for high CTE mirrors. Amateurs are successfully making aluminum mirrors 12 inches in size. Now, if those work, because aluminum cools very rapidly, so it reaches ambient in moments, but the aluminum CTE is not necessarily an obstacle.
Well, can't you just leave the mirror outside at a longer, let it just equalize, come to equilibrium in a longer time? I mean, is that the main purpose of the CTE? Because when I was in graduate school, we didn't even consider CTE. It was not until I started messing around with you astronomers that we looked into CTE, which is a good thing, because we want, astronomers to be able to use the mirrors, but.
Well, there's two things
with CTE. The first is how fast the temperature change will permeate through the mirror. And the other one is what's the nighttime cooling rate. So you want the mirror. Now, there are ways to force ventilate, as Ed is showing, to catch that up much faster than just passive sitting out there in the open. But I don't think high CTE is necessarily a damning barrier.
Interesting.
A lot of it has to do with how uniformly it cools.
Right.
So if the cooling is not uniform, then potato chips or it warps more. It becomes a bimorph essentially. And so the change in particularly focal length changes. But there's so many motorized, temperature controlled focusing systems out there now. You can program your focusing system to track the temperature. And so
forget that Lisa's problem was not aberrations. It was the mirror cracked. And
Right. No, that's
cool.
agreed. That's not going to work.
So that's what the CTE problem is matching it to whatever substrate it's on, unless you were to go all epoxy, right?
And that's what she was asking, all
Yeah.
epoxy.
Okay. Okay.
Yeah, and so just the raw CTE in and of itself, it depends on what else. It depends on what it's doing, rather than just the raw CTE. So if it's holding its shape nicely, and it just changes the focal length, say, well, that you can program your camera system to take that into account. But if it's changing the shape radically, unless you've got your magnets in place and you're doing that actively, then it could be a problem. So it's at least to my mind, it depends a little bit on what's going on.
But this is Mel, but Luke Arnold has shown even heating glass mirrors can alter the figure appropriately to improve mirror performance. He was working on, what was it, a 60-inch mirror? So, I don't think that's necessarily the end of the game there.
That's good. Interesting.
Yeah, I'd just like to say that look at the difference between low expansion glass, like zero drawer quartz versus standard borosilicates. You've got a pretty good gap there. Obviously, your gap's more and a magnitude more, but it's still both can generate equal images if everything is taken into account properly. So it's just it's a larger gap, but it's already amateur astronomers have a gap between their substrates as far as CTE.
Yeah. And certainly professional observatories keep the inside of the dome or the observatory at the expected nighttime temperature. So the mirror doesn't have to cycle through the diurnal temperature changes. And in that case, the mirror can be made out of anything.
Well, that's a good thing for us.
Yeah.
Interesting.
Yeah.
Very good. Well, I don't want to take any more time. I know we've got other things going on here, but
we do. And I think that probably looking at our questions, well, there's always one more quick question. I see from Ed. You see any alternative uses such as the sub F2 LIDAR, LIDAR, where an accurate figure is not as critical?
sure. In fact, we were about ready to write a grant proposal to DARPA, and so we were looking into all of the different possibilities, and LIDAR was one of them, and infrared is as well. So there's a lot of potential with these mirrors if you're not in the visible. That's our goal, is the visible light, but there's so many different possibilities with these mirrors. Yeah, definitely.
Okay.
The problem is my passion is teaching, and it's not necessarily the mirrors. And I love doing the mirrors, but I love teaching more. And so if I can bring my students along, then I'm going to continue this.
Okay, very good. Well, I think we're all really impressed by how far you've come.
Well, thank you.
Yeah, and thank you, Lisa. So we'll transition now to Zane, who's going to talk to us about his 14.7 inch.
I'm afraid of looking
Dobsonian.
terrible. That's why I had my camera. All right, let me start the, okay, first I want to screen share. I have only used Zoom. Amazingly, I've only actually used it maybe a half dozen times since all this started. So I'm actually really bad with it. Okay, do you see the white page with some text on it?
Yes, full screen,
okay.
Looks good.
Okay, so the first thing I just like to say is that I've been absolutely wowed by the past few presentations, and it is very humbling. And I just also like to say I'm not an engineer. I'm a 17-year-old community college graduate, and I want to study communications. Astronomy outreach is more my thing. I wish I could draw like Mel, because I love doing deep sky observing, but really deep sky observing and astronomy outreach are kind of my thing. So that's really what my scopes are built for, and that's what I try to further with my work. So given that, the best telescope to me is one that people get to look through. So I really emphasize portability and convenience And here are some scopes I've owned. There's a Coulter red tube that's sitting in my shed I'm about to give away. There's a tricolor C8 on the right, and there's a 60mm refractor I gave to somebody I'm very close friends with in the middle. And the best telescope, though, is also something that's preferably as large as possible for a couple of reasons. Obviously, aperture, the views are better, but people are just more impressed by a big telescope because it's big and it doesn't resemble the junk they got for Christmas when they were a kid. So with that all in mind, I've been interested in large telescopes since I really got started in astronomy. And I remember there used to be a time when I thought an 8-incher was absolutely huge because I started with a 4-inch Mac and then I made a 6-inch. And the thing I've really learned is that the best way to learn to make stuff, at least for me, is to build things over and over again and hope they work, and if they don't, start over and modify them endlessly, which I like to compare to what SpaceX is currently doing down in Texas with their Starship, where they have managed to build a lot of steel tubes and fill them with cryogenic propellants and liquid nitrogen and blow them up a lot of times. And last week, they finally stacked SN8, which seems to be the first full Starship that might actually make it above the ground without exploding and with 3 engines and have wings. And with that in mind, I think that the optimal telescope design is never truly achieved because you're always learning new things just from actually using it. And to me, the learning from actually using it part is really important. So what I try to do is I try to build the minimum viable product that you can actually go out and test the basics of operation and then improve on it. Because you learn, even if the overall quality of what you've built is really low, there are a lot of things you can learn just from using that are really important to the final design that might not necessarily occur to you on paper. So the first thing I did when I started hearing about sub f4 telescopes, and I started reading Mel's website, and I came to the Altaz workshop last year, and I talked about this scope a little, was I wanted to build a 10-inch f3 because, I wanted to answer these questions. Could I, a mere mortal who does not have decades of experience in building and using telescopes, use an f3 and find it beneficial? And furthermore, could somebody with average mirror making skills make an f3, which was my friend Logan. We've since fallen out of touch, but I had him make the mirror for this. And so I came up with, okay, I'm going to do 10 f3, nice size, because it's enough that you can just do some serious observing with it, but it's not big enough that it's a large investment. I didn't even have to build a mount. I just stuck it in a tube and put it on a CG5. And this was really good. The views were really nice. The unfortunate thing was that I found myself with a bit of an issue in that it's a bit longer than Mel's 10-incher, so it's really not a good tabletop telescope, but it's also not really good on equatorial or on a full-size Dob mount. And I got rid of it because I couldn't find a mount that made sense for it where I would actually use it and not have some sort of encumberment of a table or awkward pedestal legs or rotating it on an equatorial. So after the success of the 10, which I only actually used for a handful of months, I feel kind of bad. I said, okay, I'm going to go bigger. So I had a lot of different ideas. And so ranging from a 14-incher to an 18-incher. So I thought, what if I do a meniscus with 0.75-inch plate glass from Logan? And Logan tried to make a 16-inch meniscus, and that didn't go very well. So that was out. And then I said, okay, what if I do just like an f3.5? But the thing I found with that was that the field of view was getting kind of small and the scope itself was getting kind of big. And I didn't really like the idea of a real thick Pyrex mirror. So I talked to Steve Dodds at Nova, and he happened to have one of the last few of these 14.7-inch semiconductor blanks, which there was this company that was using them for some sort of semiconductor thing. They get worn out and they have to be replaced. And so there were just piles of these things. And Steve and a couple other guys bought like hundreds of them and made them into mirrors. And they're 0.8 inches thick and they're made out of solid fused silica. So they have a number of advantages over a glass mirror. Of course, there's CTE, but they're actually, I did some research, and quartz actually has a higher modulus of strength or something like that than a regular Pyrex. So I got away with a weaker mirror sill than I could have otherwise. And it's the first of my scopes that actually didn't come in massively over budget or massively late, which was nice. And it's really exceeded my expectations. So with regards to the field of view, which I'm sure everybody here is familiar with RFTs, but I just thought it would be fun to show because I have an observatory near me with a C14 and the maximum field of view of the C14 is 138% smaller than the, well, sorry, no, the 14 has a, my 14.7 has a 138% larger area than the C14 in the observatory. And I get about 70% more area than some of the people with 14-inch Dobs who I met with that are usually F4, F5, and they're using a 31 Nagler or 41 Panoptic to get the widest field. And I like I really like the ethos in the 100-degree eyepieces, because in addition to the fact that you really are able to game these laws of physics and whatnot to get the most field of view out of an exit pupil, the immersion factor is just amazing, combined with that super wide true field of view. And that's really what I've been trying to get with this scope, and I think I've really succeeded. So I build by trial and error, because I'm not very good at math and I'm not very good at project management. So originally I was going to actually build it out of maple and aluminum and make it really minimalist. I was going to have like an A-frame tube, and I was going to have a maple mirror box. And I gave up on that after trying to glue up maple panels and finding I had about a 50% success rate at that. And the issue is, when you're trying to make a mirror box out of maple, you're going through about $50 to $70 worth of maple for every one of those. So if you mess up 50% of that box, that's 25 to 35 bucks worth of material that you're throwing out. And I just didn't find it worth it. And then I wanted to do one at a mirror box at a 1/2-inch plywood where the upper tube assembly nested in it. But the problem was there that I just felt that the box had a tendency to want to force itself into a parallelogram. And if I was going to brace it so it wouldn't do that, it was just going to weigh as much as a 3/4 inch. And I like 3/4 inch plywood because I can use biscuits on it, and I don't have to worry about screws poking through the other side if I put handles. And then I thought, oh, I'm going to put it in a concrete form tube. So I actually went and bought concrete form tubes, and I'm all ready to go. And then I actually tried to put it in the car, and I just didn't like the idea, mostly because I couldn't see when I backed out of my driveway with the tube in the back. So then after a lot of work, I bought the mirror in November. I had it in hand by Christmas, and I kept messing around for most of the winter. I finally came up with this horrifying looking thing that vaguely resembles a Dob, because what I did was I remembered I had a 12-inch Dob that I had built. I had kept most of the structure, so I said, okay, let's just shove the optics in that. I stole the bearings, the mirror box, parts of the rocker, the truss poles, the truss connectors. I think even the ring there for the upper tube assembly is stolen from the 12. And I used a drum shell for the upper tube assembly, which I really like. But this thing was terrible because I siliconed the mirror to its cell. It was really heavy. It didn't balance. The bearings were too small. And I really hated it. So I used that for like a month or so, though, because I wanted to get an idea of just observing at low power with the scope, even though the mirror being glued to the cell had something like 2 ways of astigmatism. So you basically couldn't use anything more than 7.2mm ethos on it, which was really bad. But I used it a lot, and I kept writing down all the issues I was having with it and the things I didn't like. And I spent a lot of time looking at people's scope builds online. I was really bored. They hadn't really moved any of the classes to Zoom at my community college I was at, and I didn't really have anything else to do. So I was observing with this thing nightly just to see what was wrong with it, more or less. And after a lot of work, about 2.5 months, I came up with this thing. So I call this the Mark 10. You'll notice the version numbering here. The Mark revisions are basically any major change that I think makes the telescope no longer really resemble its previous version in the field. So I came up with these giant altitude bearings, which were cut by a guy with a CNC in Long Island. I stole the design from New Moon for those. And they're actually, I think they're 26 or 28 inches. They're really huge. And I sort of went with Mel's folding Dob design, except I didn't make it fold. But the idea was I wanted to keep the whole mirror box assembly low, and I really didn't want the center of mass to shift too much. And I made my own upper truss brackets, which are terrible looking, but work really well. And I put a curved spider in. I didn't have that originally. And the scope went down to 48 pounds. There's still a lot of issues, though. And one of them was the mirror cell. I had it siliconed. Then I actually had the mirror on tabs of Velcro to hold it to the support points. And then I just had it sitting on these edge supports that were really designed to help you center the mirror, not to actually hold it in place. So this mirror cell is weird because I was uncomfortable with the idea of making one. So I just bought one from Aurora Precision. Aurora Precision AZ mirror cells are not made for thin mirrors. Also, they don't really recommend that you buy the 14.5, even though they offer it. And the interesting thing was, I was able to make this work. I talked to the guy, Nathan at Aurora, and he came up with these little mini roller bearings that are made out of Delrin. They keep the mirror centered, and it's able to spin around in the cell. And it only has about a 1/10 of a wave of astigmatism, and that's because the edge support points are not positioned at quite the exact degree angle they should be. But considering that it's a cell that wasn't designed for this, I'm pretty happy with it, and it's a 1/10 of a wave of astigmatism. I really don't care. And the other interesting thing, going back to the quartz, is that because the quartz has a higher modulus of stiffness, the plop gave me, I think it gave me about 1/20th wave error with 6 points. And in practice, it's probably slightly worse than that, but there's no print through with 6 points. There's no trefoil issues. There's nothing that would indicate that only having 6 points of support is a problem. And it looks like I lost the photo of the edge supports or something. I'll just pull that up real fast. Actually, no. Oh, it's there. It's right there. I don't know why it doesn't show in the slideshow. Whoops. Let's go back to there. Yeah, I don't know why it doesn't show up. So then I did a lot more revisions. So here's just the sort of list of them. So I put a moonlight focuser on there because I had a helical Crayford from Kiln Optics. I love those focusers. They do not work at f2.9, especially at high magnification. I put magnets on the upper tube assembly so I could transport the whole scope compacted in as few trips as possible. There's an EQ platform under it, which I know is kind of cheating, but I didn't really feel like doing a whole drive system on something this small, actually. I cut down the mirror box, the rocker box, and redid it. I put a lot of baffles. There's a baffle behind the primary mirror. And the scope, even with the platform, is now 51 pounds. So it gained 3 pounds in tracking, and it's actually more compact now than the Mark X, which I find pretty cool. And it actually fits in a passenger seat if you stack it right, which is pretty cool. I haven't driven with it like that because I don't really want to, but it can. I was actually contemplating shoving this in a box and shipping it to the Texas Star Party or OSP before those got canceled. And I actually really just finished all these upgrades this month. The baffling and the EQ platform are really recent, but I'm really liking it so far. And obviously now the question is, well, what have I seen with it amidst all these upgrades and all that? And I can tell you that it more or less does everything you would expect a good 14-incher to do. But there's also been some stuff that's surprising. So I saw Galileo Regio. I've seen Galileo Regio on Ganymede, which is I've seen it with other scopes. I've seen it better with the 16 that I had, but you can see it. The thing people don't realize is that Galileo Regio takes up like a third of the entire face of an entire hemisphere, or close to half. So it actually is pretty easy to see. You can tell that the top or bottom half is darker than the other. The Yankee division and Saturn's rings. But the first thing that I really went deep on with this was the Heart and Soul Nebula, which I don't think Mel has a sketch of this. And my rule was, if Mel doesn't have a sketch of it, I must not be able to see it with this. So I went for the Heart and Soul Nebula anyway, because I was talking to one of my friends and she had just done a photo of it. I was like, oh, I'm going to try that visually. And you can actually see the heart structure. I can't draw. I really wish I could, but it's really cool. You can see it. It's very dim. It's like an integrated flux nebula, but you can see it. Pickering's triangle in the veil. G1 and G2 and Andromeda. That was cool because I went for G1 and I saw that G2 was there on the charts, and G2 is barely visible, but it's there. Individual H2 regions in a lot of the spiral galaxies. Another interesting thing that I found was you could start to see color in globular clusters. This one I really didn't know if I was imagining, so I actually I was with some folks observing, and I asked some of my friends to take a look, and they all saw this kind of warmish tone. It's not really color. I feel like that's the wrong word. You can't tell, except in M4. M4 has some red stars, but when you look at M13 with a scope this size, it's doing something to activate your cones, but not a lot. So you can kind of tell there's this warmish tone to it, but I can't tell if it's yellow or orangey or what. And obviously the stars themselves are different colors, but it is a warmish tone. The North America and Pelican Nebula look really cool. And I've seen I just saw the California Nebula for the first time with it, like last week. And I have been starting to hunt for the integrated flux nebulae that Mel loves to draw. including the one near M31, and I think I've seen a bit around M13, and the Central Star and M57. I'm not really that good of an observer. I like to use Sky Safari on my phone as a chart, so I'm probably blowing away a good chunk of my dark adaptation on a regular basis. I have mediocre skies of, that's the other thing. My skies are barely Bortle free. They're technically Bortle 4 on the map. I've measured Bortle, that they're probably something like Bortle 3. And I drive 90 minutes up to Litchfield, Connecticut for that. My house is Bortle 6. It's terrible. And I guess the thing to me that's really cool is not that you're seeing this all with a 14-inch. It's that you're seeing this all with a scope that weighs 51 pounds and you can set up in a couple minutes and tracks, and you know, you can get a 1.7 degree field out of, and it can, you know, it can really pull these faint objects and do these high resolution things and do wide field stuff. And I didn't really plan to make it all in one telescope, but I sort of ended up doing that. Obviously, collimating it well enough to do these high resolution things takes a while. If I'm just doing deep sky, I won't, and the seeing's not very good, I won't spend as much time collimating. But that's a challenge. I wish I could explain how it works, but I honestly, I barely understand how to collimate the thing myself. And I would have to, it's a weird process. So obviously I've not even gotten close to exceeding the limits of what this scope is capable of. There's a lot more things I'm still looking at with it, and a lot of things I'm trying to do. I've split some subarcs and double stars with it, which has been interesting. But the thing, I am really hoping to look at more integrated flux nebulae, but I'll admit that my favorite thing to look at is galaxies. And, you know, I think the guy that was being talked about last night, Jimmy, he likes to use a 36 and the 48. You know, galaxies, you can always have more aperture. Who cares about field of view? So with that in mind, I started coming up with a larger scope. And initially I wanted to do it. I was actually going to do a 17.5-inch Dob out of a Coulter mirror just for galaxies. I didn't really care about anything else. And then I decided that wasn't enough of an upgrade to waste my time and money on. And then I said, okay, how about a 20 or 22? And I did all the math, and I found that the gain of one of those over a 14 is really not a lot, especially because I think the 14 has enhanced coatings. So I really couldn't come up with an economic justification for that. And then I talked to Nova about a 24-inch f3.5, and it came in about $5,000, which was pretty cheap, but not affordable for me. I pay for all this stuff by writing telescope reviews. Pretty much, that's how I do this. No money from family or anything to finance this. This is all me. And the thing was that, you know, I could have probably bought the mirror, but I didn't want to buy a mirror and then throw together a structure out of junk. So then I got an email about how he had made this 24 f3.5. and it had gotten damaged in shipping by UPS, and I'll show you a picture of that in a minute. And I got a very hefty discount on the mirror, so I said, okay, how about I build a 24-inch? And the funny thing with this is that it has to fit in my mom's Ford C-Max hatchback, which I don't know how many people here are familiar with the Ford C-Max, but it's not a big car. I don't have a big Ford Transit like I think Howard has. I would love one of those, but I don't. And so I've been faced with this monumental problem of how to fit a 24-incher in a hatchback, because I really don't want this one, especially the 14. I'm good with just being for me, but part of the reason I added tracking to the 14 was just for astronomy outreach once there's more of that to be done again. But this one, to me, I really wanted a scope that I could get out in a moment's notice and have set up fast, and wasn't something I was restricted to using a couple times a month or with a multi-person setup or in my yard. So I've been spending a lot of time trying to figure out how to get this in a hatchback. And there are some weird compromises, like the altitude bearings have a cutoff at the top. You'll see there's a render of them in a second. That they have 15 degrees cutoff, because that saves me about 3 inches of clearance. And that means I can't point right at the horizon anymore, but who wants to do that? And I also welded the mirror cell on this, which was terrifying. So here's some more pictures of it. So on the upper left here is the primary. as I got it. I was a little afraid that they were going to completely destroy it, shipping it to me from Nova, but they didn't. And here's a dual pass auto collimation image of the primary. It has a little turn down edge that needs to be masked down, but considering the price I paid, I don't really care if it becomes a 23.5. And that chip looks terrible, but it didn't affect the figure at all because it's a clean. It came right off the side, which is interesting. I did a lot of reading on glass fracturing after this happened, and there's no stress or anything in the mirror itself, so there's no. I'm not worried about anything long term. And on the upper right here is my mirror cell. Now I started working on this in May, and at the time I really didn't have a lot of help with welding. I had one of my dad's friends come over and show me the basics, and then I threw this together, the tailgate of it, and use a cable sling, which I would have preferred 90-degree edge supports, but the edge support calculations were a lot harder for me to do, so I just went with the sling because I can mess with the sling to my heart's content very easily. And those are some support points on the bottom right. And on the left here, you can see the weird little cutoff on the bearings, and you can see it actually removes quite a lot of material, which really helps with fitting it. And in the middle here, there's the field of view comparison, which I always think is interesting because when you're using scopes, typically you're thinking in terms of magnification, and Mel's got this idea of thinking about attendu. And the thing I like to think about mostly is just area. Even if you say, oh, it's only double the magnification, double the focal length, the interesting thing is that's actually 1/4 of the area of the 14-incher, which means that if I am doing my usual dead reckoning of finding deep sky objects with a Telrad, I have about 1/4 of the likelihood that my target's actually going to be in the field of view when I point it, which is a funny thing to think about. And I'm in the final stages of this scope, really. The sides of the rocker box aren't in this photo because I cut them to the wrong size and have to redo them. And the only other things that have to be done are the focuser board here. I might trim these struts down. I'm waiting for a new spider. The old one was not heavy duty enough for the secondary, and I have to put the support points in and put the mirror in, and then and build the wheelbarrow handles, move the scope around, then I'm all done. And I guess to me, I'm a little bummed that I didn't have the ability to make this an F3 or an F2.8 or something. I really wish it was, because then I could really avoid the ladder, or the step stool rather, for me. But I'm pretty happy with how it's going. I think it's going to be good. I hope it's good. I'm a little concerned about that. And I guess I was a little afraid to experiment as much with the as I did with the 14, because with the 14, everything is it's a big scope, but everything is small, and you can everything can be picked up with one hand, and you can put all the parts of it on one table, and taking it apart takes 5 minutes, and nothing's the size of a person. This I didn't want to mess around with as much, because tearing it down and redoing it is kind of a trickier proposition. So the whole build, destroy, repeat thing is a little more intimidating. And I guess I hope that if anybody is inspired by this, that they're a little more courageous than me when it comes to that, because I feel like I'm probably going to end up regretting that I didn't get more experimentative with the design here. But I'm looking forward to it, and I think there are probably going to be more upgrades to the 14. I've already come up with a few. I'd like to do I'd like to have some sort of iris on the focuser for baffling purposes, and I could actually stop down the aperture. And I need to make an off-axis mask for it too. That's about all I have. So I just wanted to thank everybody for inviting me to this, and if there's any questions, I see that there are a couple in the chat here, so let me just read those. Homemade mirror cell, yes, I did weld that. This was the first thing I ever welded, other than, well, I bought some extra square steel tubing and welded that together first. It's with a stick welder, and I'll admit it's not the prettiest, but it is pretty strong. I did put threaded inserts on as well. So there's a mechanical connection too as a backup and a failsafe. But the welds are pretty strong. I was able to put the mirror. I put the mirror cell in like a vise basically, and then stood on the end of it, and nothing happened. So that's more. I weigh more than the mirror does. So if it's gonna break, it's gonna be from me, not the mirror. Yeah. I did use plop. It's an 18 point. Those triangles that you saw there are not actually the ones I'm using. I decided those were too thin, and I'm using 1/4 inch aluminum for the plates. Some of the cell dimensions I did just steal from the Dobsonian telescope because I was lazy and I couldn't figure out the tailgate bar, so I ended up using just some addition and subtraction to figure out the placement of the tailgate bars, because plop doesn't really tell you that. Because it's not designed to. Plop is confusing. I still don't fully understand it.
So Zane, you seem to go through telescopes as fast as most people go through, I don't know what, a pair of shoes. So
yeah, I've owned 180 actually. My 180th telescope was today. I got an ETX one. I got an ETX 125 that I got it very cheap because I was told the motors don't work. The motors do work. I'm not sure what's wrong with them though, because the battery connection just broke, and so I've been powering it off of DC, and the scope just randomly decides to slew itself in RA for no reason. Yeah. I've been trying to figure that out. But yeah, I go through a lot of scopes, and that's part of how I learn about designing them, is just by tearing them down. And
so my question is, are you planning on keeping your 14.7 inch?
Oh, yes. The idea with the 14 was I wanted to build, and the 24 too, but the 14 inch definitely for me was I wanted to build a scope that I didn't ever want to get rid of or scrap. Because back when I started on the 14, I was still considering a lot of different things for college. So I was like, well, I want this scope to fit under a bed in a dorm. I want this scope to fit, if I have to fit it in a passenger seat, then it should. I want to be able to put it on a cart and wheel it down an elevator if I'm in a dorm. Now those aren't problems because I'm going to a local school, but at the time that was very concerning. And regardless of my living situation, I want to be able to use that scope. And I've been improving it like crazy, because if there's ever a day when I don't have access to a shop anymore, I don't want to be sitting there going, oh, this thing really frustrates me. I want something different.
Well, good. It looks like it's a really good scope, and certainly from your observing reports, and I'm glad you like it enough to think you're going to keep it.
Yeah, that is a rare thing for me.
Yeah, well, and then like you said in your presentation earlier, no scope is ever really finished.
Yeah,
so
definitely.
You'll keep tinkering.
I will be modifying it forever.
Oh yeah.
I will probably be modifying it when I'm like 70. I'm sure. I don't think there might not be any original components at that point. It might be the ship of Theseus, but I will still be modifying it. I
can well imagine how that goes. I have a telescope that's gone through that type of metamorphosis since I was 14. So yeah, I get it. So any other questions out there, or is it time for our short break? No? Okay, let's take a 2-minute break.
Actually, there are a few questions on the chat that Dan and I asked.
Oh, there are more? Hold on, let me.
Oh, okay, yes.
I see. Yeah. So, am I going to be a professional astronomer? No. I actually, for me, like, all this is really kind of a side thing. I really enjoy bringing astronomy stuff to the public. Actually, I don't know. How do I mess with the screen share here? I have no idea. Let me just go to, let me just show you guys something. Where do I don't know. Oh, no, wrong one. Screen, no, new share. I'm going to just do the whole screen here. There we go. One of the big things for me with this 14 inch actually is that I have one. I don't know if you can see this here. Can you see Google Chrome and Reddit?
Yeah.
I am the top/r/space post of all time, and actually one of the top Reddit posts of all time with this scope. And I look like an idiot in it. So this is going to be me till the end of time. This photo. I look terrible. I'm not wearing shoes. The ground board's not painted and it's the ugliest version of the scope. But what I loved about this, besides getting my 15 minutes of fame, was that I had so many people messaging me about how they could build their own scope or where to get a scope. I was replying to people like who were seriously interested in building their own scope or obtaining one, but a lot of people interested in building for a month. I had people message, a month-long backlog of messages about building a scope. And there have actually been a few people since I posted this who built Dobsonians directly as a result of this, which I'm really proud of. And to me, that's the real fun of this. I can take the 14 out to observe with, or and take it out with my friends to look through and show them the views all I want. I've done that quite a bit here. But to me, this right here is infinitely more valuable than any of that, because this is not, it's not just inspiring people to make telescopes, and it's not just inspiring people to do astronomy. It's showing people that, you can, I think that this workshop does that too. It's showing people that you don't have to be a guy in a university necessarily. You don't have to be this professional. You don't have to be on TV to do really amazing stuff. You don't have to be a trained professional to build something. You don't have to, you don't have to spend thousands of dollars to have a good telescope. You don't have to, and you can make something cool or do something cool with almost nothing if you have the inspiration and make the effort. And that to me is the really valuable thing about building these and about doing astronomy. Everything, like, and I think there's also a lot of skills to be learned here too about not just engineering, but I think I've learned, and this is something that's really helped me, is I've learned a lot about project management, budgeting, and all of that stuff from building these scopes. I've learned little skills that I might I learned how to weld from making the mirror saw. I could have cheaped out and just gone and bought one. It would have cost me more, but I learned how to weld. I know how to weld now. I think that one of the great things about telescope making is it's very interdisciplinary sort of part of the hobby, because you're learning all of these different skills at once. You're learning about everything from project management to all these, to different types of mathematics, to optical testing, to aesthetics, to just getting the word out there about this stuff and trying to spread your ideas. I think all of that is really important. And I think that these ideas of doing stuff yourself and project management and learning how to share information about a project are things that I think in today's world are kind of lacking. And I think it's great to be able to give people an interesting way to get into these ideas and learn these skills that I think are really important for everybody to know. And that's really what this is about. To me, it's much more than the telescopes or the stuff you're looking at, or even that it's astronomy.
That's a great answer. That is really a great answer. Thank you very much for that. So, okay, let's take a 2-minute break.
All right, thank you guys.
And thank you very much, Zane. That was a terrific presentation. And we'll come back in a couple of minutes and listen to Tong.
Are you still by your computer, Zane?
Yeah, I am.
That was a great presentation, and
Thank you.
it's funny your name came, your name, although I didn't use your name, came up today because someone reached out to me who saw my presentation on Artemis a couple of years ago to the Royal Astronomical Society here in Toronto, before it was actually done, and he's writing an article about the state of ATM for one of the, basically the Canadian equivalent of Sky Telescope. And so he was kind of, in quotation marks, interviewing me, asking me a bunch of questions about the state of ATM and whether ATM is alive or dead. And I said, well, one of the things that I said, was that it's changing because, of newer technologies like 3D printing and whatnot. And, and fewer people are pushing glass. But there's so much innovation going on in the actual putting together of these things. And I used you as an example of, while, a lot of ATMers are older, there's like, there are these younger kids that are doing exactly the same thing. So it's inspiring and, far from dead, far from a dead art.
Yeah, I actually, that Coulter I showed in my first slide is actually, I'm talking with a guy who lives down in New Jersey who's 16. He wants to do a truss daub as his capstone project for his senior year, but he wants to get started on it now. And he picked up an 8 earlier this spring after seeing my post on Reddit, and he said, he really wants to build something for his capstone project. So I've offered him the Coulter and I have some spare aluminum tubing because he has a limited budget for it, and he's probably going to come pick that up. And I think with what's great, I think that what I've been doing is what I've really realized is there's a lot of, if you build it, they will come. Like as soon as I made that post, I didn't have to do anything. It already reached a lot of people and it got a lot of people inspired. But I think that it's really important to sometimes to go the extra mile. And sometimes with that stuff, I've done a lot of work writing telescope reviews, where I really try to stress that ultimately, I don't talk a lot about making scopes on the site, obviously, but I talk a lot about how ultimately this stuff is really best if you modify the hell out of it and don't just leave it as out of the box. Like I talk about, and I review, like there's one scope I talk about sanding the dew shield and putting flat black paint on it. I talk about flocking a ton, because I think that's really important because the black paint they use in most commercial scopes is horrible. And I also give away, I've actually given away a lot of stuff. A lot of people don't know that because I think if you talk about doing it all the time, and then you just get people who want stuff who don't need it. And also it to me, it just kind of turns into sort of virtue signaling if you do that, and diminishes the point. But I've given away probably 15 scopes. I gave quite a few away for Christmas. There were a lot of people my age who were talking about online and talking about how they were really disappointed because they'd asked for like an 8-inch daub for Christmas and they got like some junk refractor. So I sent out a few scopes that I had gotten good deals on. Just today I gave away an ETX90 to a girl who had gotten a G Skyer refractor. It was horrible. I saw one, I was offering to help her with it, and I was like, can I have a picture? And I saw one picture, I was like, oh, forget it. And I just grabbed this ETX90 I hadn't been using out of and I gave that to her today. And I think also that there's this idea too of you need something fancy to do interesting things. Like a lot of people my age want to do scientific stuff that, like, not real science, but they want to do a proof of concept. They want to measure the eclipses of Jupiter's moons. They want to measure the angles of double stars. They want to do parallax of the moon from different locations and that kind of stuff. You really don't need much at all. I have a friend who goes to Cornell, who she wants to do some sort of project with an Orion Skyscanner I gave to her. It's a $100 4-inch tabletop daub. And I think she's mentioned doing astrometry of double stars with it, which is pretty cool. I think that I'm not the kind of person who's good at the mathematics side or doing any kind of citizen science, but I think that the cool thing is that there is a lot of that to be done. And I think that that's really motivational for people who might live in the middle of a city and only be able to afford a little scope. But even then they can, they can make a micrometer put on their eyepiece. There's all kinds of little projects you can make for astronomy gear that are really cool. And I actually think that a lot of the times the homemade supplemental stuff and accessories is more important than the scopes themselves. Like I actually think that it's almost better to shove better baffling and flocking in a commercial daub than necessarily go out and build your own in a lot of cases until you start getting to. I think unless you have some weird use case, unless you're like us and have a lot of interesting and weird use cases, a lot of people could just do a lot with modifying things that already exist. And that's what I do a lot too. I've built a dozen scopes. I've owned almost 200 commercial things. And I've spent a lot, even though most of them I've sold, I've spent a lot of time tweaking them and learning how to do that. And that helps a lot with design. Like, I think I learned a lot about stray light control from working with a lot of commercial scopes that didn't do the best job at it and learning how to fix that. And I think there's a lot, I'm sorry, I'm very disjointed. I'm just like speaking what comes to mind here.
That's okay, Zane. It's time to move on.
All right.
to
no worries.
Tong's
Yeah, sorry, I
presentation.
talked for too long.
So
I'm very excited about this one.
you made some really good comments there, and so
Thank you.
That's all right. We're not there's no penalties for going over our time, except for maybe some of us go to bed a little later. Anyway, Tong, if you're ready.
Yeah, okay. Can you see my screen?
Go ahead. We see your screen. We see all your slides on the side.
Okay, it's good. So I'll start my slide. Okay, you see it? See my slide?
Yep. Looks
okay,
good.
Great.
Yep.
Okay. And we have been working on the UL40 F3.3 for about, I think, more than 2 years. I gave a presentation last year, but after another year, it's still a work in progress. So here it is again. And it's a slow process because the mirror is making it very slow. So we are close to finish the primary mirror, and but not quite there yet. It's at this time it's a quarter wave, but we did finish the secondary mirror. So the design, you see still the paper on the paper, but the mirror is almost there. So I'll give an update on our design and the mirror production, and some other thinking and on the future direction of this project. Okay, this is the design. It's based on Mel's the website. It's the prime mirror is 40-inch, and the focal ratio is 3.3, and the diagonal size is 11. And it's 11 by 12. It's not exactly a round mirror, but it's close. By the way, this mirror is our 6th 1 meter mirror. We have made a 5 1 meter mirror already. And the first 3 are the first 3 are the collimators for NASA project. And the 4th one is for the Australia Astronomical Society of Victoria, and it's for their 1 meter telescope. The scope is working very well in operation at the moment. That's a simple history of our 1 meter production. So this mirror is actually our 6th mirror, 1 meter mirror for this 40-inch 3.3. Here's the comparison of what's the advantage of folded. This is designed as a folded Newton. So it's and the advantage is the lower eyepiece position and larger focal ratio for the primary mirror. So it's easier to make. because it's already very fast at 3.3. It's very difficult to make already. If we have a regular Newton, it will be even faster. The mirror is much more difficult to make. The second mirror in the design, we can use a round secondary mirror, and much easier to make other than the regular secondary mirror. However, the disadvantage is a little bit more difficult for the baffling and a little bit larger for the secondary mirror for the obstruction ratio. But I think we can all live with that. It's not such a big deal. Okay, this is a primary mirror, and it's at a quarter wave at this time. It's almost finished, but probably still another month or two. So this is a 12-inch secondary mirror. It's still a sandwich mirror. So you can see that we have a very strict the band, interference band. So it's a very good quality. We feel it's at least a quarter wave overall. Okay, this is our design of the telescope. You can see that at a 40 degrees above the ground, you need no ladder. And the scope looks familiar, Howard, right?
It does look familiar in some ways, yes.
Okay, yeah, we took a lot of design idea from Howard's 20-inch telescope. So you can see the overall design and the drive system and even the upper cage. So we used to use a single stage, the upper case. So now we found it's too difficult for the baffling and for the folded Newton. So we have the two rings with a smaller truss tube to have a much better, easier baffling. And for the scope at 45 degree, probably need a one-step ladder, and at most a 3-step ladder at Zenith. So it's pretty reasonable for 1 meter telescope. And the secondary baffling is it borrows some ideas from Dan's 28-inch, and the Rayner's there's a low rider, a 20-inch low rider made by Rayner. You can see that there's a baffle for the focuser that will further reduce the requirement on the secondary baffle. So here are the baffle design. So it had 3 parts. The main surrounding baffle, so that's a bigger one, the largest one. The second part is the center is a vertical baffle, and then the focuser baffle is around the focuser. And it's a straightforward and very easy to make, and the result is pretty good. And based on the CAD. This is a secondary mirror support, and the mirror is here is a solid mirror, but we will use standard mirror. Use a 3-point support. And for the primary mirror, it is 27 support structure, and similar as the one Dan is working on. Howard, is that you are using 27 support, right?
No, I'm using an 18.
Only 18. Oh, okay.
Yeah.
So we use 27 support points. Okay. So here's the lateral support. It's very much it's similar to what Dan and you are working on, but kind of a simpler the design. I feel it's still adequate for the edge support, and so you have the bigger the central bolt with another another plate, and it has two smaller pivot support for the sandwich mirror. So we need because we have the upper plate and the bottom plate, so we need a pivot support on each point. So the overall is only 8 point for the entire for the lateral support. Okay, you can adjust the height of the support, and it's pretty straightforward. And for the mirror support. Okay, here again, I'm reviewing. This is some design little iteration for the drive system. This is Howard's the 28-inch drive system. And it's a attitude drive, and here's the azimuth drive, and here's the UL20. Bruce made a similar drive system for 20-inch for scopes. So you can see there's 2 shafts, and also, but it's not even leveled because of one of the shaft need to be lower to prevent the scope to fall over. It's okay. This is version 1, the friction drive. And he made a second iteration and using the timing belt. And how actually your first revision is timing belt, right?
Yes, I tried several timing belts. Yeah.
Oh, okay. So this is actually the Bruce is going different direction. He used the friction drive as the first revision. This is his second revision. He used timing belt for both altitude and azimuth. And one reason, the advantage is less sensitive to the balance. So it doesn't need that much balance on even you change the eyepiece or equipment. This is it worked well for his application. So I'm not sure what other so what kind of disadvantage you have with the timing belt as a first revision as yours?
Well, I only use the timing belt on the azimuth, and to me the disadvantage was, and it was relatively small, but it was something that, at least the way I made it on my scope, it needed to be adjusted fairly often, because the scope would go around. If you turn the scope 360 degrees in one direction, 2 or 3 times, the belt would tend to walk up or walk down off of the azimuth base.
Oh, okay.
Yeah, and so I just wanted something I didn't have to worry about.
Okay.
So I went away from it.
He used some retainer to solve this problem. So the belt will not move. So I show you the. Oh, also another reason is that it doesn't want to. He tried to avoid the slippage of the friction drive. It's that's another reason. It has 2 reasons. One is the balancing. Another is the slippage. It's okay. Here's the clutch for his the attitude clutch. So there's a timing belt, and also there's the roller to against the timing the timing roller. It's pretty simple. Okay, here's the drawing of our first revision, and based on the timing belt. And you can see how it's here is some the retainer on the timing belt to restrain the movement of the timing belt. Yeah, this is a very simple, the brief update. This is still on paper and not much. And the mirror is almost done, so we will probably use Howard's yours design. It's a friction drive, not the timing belt. And in the real design, it's one of the reasons is probably the periodic error of the timing belt. Another is a vibration during the slewing that could be from a result from the timing belt.
Yeah. The other thing about a timing belt is that you need to get a really good timing belt that doesn't stretch out over time.
Oh, okay.
You need to have it under enough tension that you don't get a lot of backlash just from the stretch of the timing belt when you move the telescope.
Okay. Okay, that's good point. So it's what?
Yeah, my last timing belt was carbon fiber reinforced, and that was by far the best one.
Okay. Yeah, that's good point. So here, what's the future directions for this project? Because we have some new requirement, new customer, and asking to have the capability of the research grade patient. So that's mainly for the high resolution encoder. In particular, they want a 0.1 arc second tracking capability. That's pretty extreme. And so the one of I discussed that with Dan already in quite a few emails. Here's the current thinking for this direction. So we will use a backlash free drive system with harmonic gear like the power you use for your system. And also we will use the high resolution range encoder. And I know the scope is not, the mount is not accurate. So it's we don't expect the extremely high pointing accuracy. However, it is my thinking is as long the scope is the move smoothly and without high frequency error. So it's everything can be the tracking accuracy can be achieved by the it's I'm sorry, by guiding. So it's the high frequency guiding, and so we just want, as long as we have enough resolution, enough pixels per revolution. So it's here the one we have two options. One is the 100 diameter, 100 meter diameter, the Renishaw ring that will result have the 6 million ticks. Another option is the atom encoder is with the 32 million ticks. So it's even for the Dobsonian, and it will have quite a bit the mounting error. So it's even with all the, I'm not sure how well the model will work. And probably it will help. However, the assumption is we as long as we have enough resolution, and we will achieve a very very good result on the tracking with guiding. But that's just the assumption. We will have to wait and see. Okay, here's all we have. Oh, here, yeah. This is a Dan's bike motor with the 32 million atom encoder, and so this is the idea. I guess okay, maybe we can just do something with our scope with atom encoder. Okay, thank you very much. That is it for me today.
Okay, so Dan just posted a comment on the chat function, and he said he's tested the atom encoder from Renishaw and it works great. But the read head adjustment is really critical. Dan, if you can speak more to that, if you could put on your microphone.
Hi, everybody. It's really quite economical. So if you can design a good mechanical system that holds the read head very closely with the little glass disc that comes with it, it's a really good option. It comes with 32 million ticks. I don't know, I guess that's probably about, I'm guessing about 25 ticks per arc second. So that's pretty good resolution. It's not nearly that accurate. It's probably, I'm guessing, about 2 or 3 arc seconds in accuracy. And the hope is that it's not cyclical based on the interpolation, and that it's so like point XP or something else can take the errors out of it. I put one of those on a German equatorial mount, and it worked, and it's never failed me. It's always worked. It's a pretty good German equatorial mount, but I had a low a small focal length telescope on it, but it really did work well. I never had any problems with it at all. But it was a good mount. So I can't think of the brand right now. I'll post it when I found out the brand, when I remember it.
Okay, Dan, my question is, if the accuracy is 12.3 seconds, is it possible to achieve a 0.1 arc second with guiding? So all we need is a resolution, not an accuracy in our case, because the closed loop will be the loop will be closed by the guiding, not by the encoder itself. Is there any logic of the loop? The loop code?
Yeah, if you close the loop with the sky, which is guiding, it's possible to get like, 0.1 arc seconds is probably pretty, it might be a little optimistic. The seeing shifts around quite a bit more than that. But hopefully you get round stars. You would get round stars. Probably in realistic, maybe 0.2 or 0.3 arc seconds.
Oh, okay.
And that's not going to have much to do with the encoder, more the motors and the response of the servo system and everything.
That's true. We will certainly use a there's no backlash. We use a harmonic drive and to make sure there's nothing.
Yeah. Backlash is the enemy of the people. I tell you that.
Okay.
It's the worst one.
Yeah, I know. If you have backlash, there's really nothing you can do about that.
Yeah.
Okay, thank you so much for your comment.
Okay.
So when do you expect to have this telescope completed and ready for action?
Well, I hope that will be another 6 months or something like that.
Okay.
The high resolution requirement actually is for 24-inch telescope, not for the 1 meter.
Mm-hmm.
But we will use the same design for the 24-inch telescope for the high resolution. The encoder will put over there, not first for the 1 meter.
So I have a different question for you now. You earlier talked about the secondary flat, and it's 11 inches, 11 by 12, I think you said.
It's right. So we made a 12-inch round circular center in the mirror.
Okay.
It's a 12-inch.
Okay, and which, as you said, is probably much easier to make than an elliptical diagonal.
Yeah, absolutely.
Is that a product you would be willing to sell separately to people?
Oh, sure. Yeah, if there is a need, we can certainly sell that.
Oh, yeah, because I'm thinking of Mel right now with his 30 inchers, and then it's 42 inchers that'll be coming up at some point. I know getting big flats for these big fast mirrors is potentially one of the biggest and most expensive parts of the project.
Yeah, we feel as long as the circular round mirror, it's much easier. It's very much like you make a regular mirror.
Mm-hmm.
Yeah. Of course, you need some new technique, but overall it's much easier than the real secondary mirror. It is the same mirror, same process we use for all other mirrors.
Okay, excellent. That's good to know.
Yeah.
So, is there any other questions out there?
On that bicycle motor, was that the center direct drive motor from a wheel-driven bicycle?
Well, it's for Dan.
That question is for Dan Gray.
Okay, Dan.
Hi, Bill. Yeah. Any three-phase motor, you can take an airplane, one of those, hobby motors on an airplane, or you can take a bicycle motor, and you can take anything at all. If you put a good encoder on it, you can control it with a Force 1 controller, and that's what I was using.
Cool.
Yeah.
I haven't finished my 16-inch telescope yet, and I'm thinking that I want to put direct drive motors on it, but I don't want to spend the money. So.
Okay, well, we'll just have to get in touch. I can help you out a lot on that.
Well.
Did you see my presentation on
yes.
On Thursday? Was it Thursday?
Yeah, it was.
Yeah. Yeah. Okay. Yeah, it's a little expensive, but boy, the rewards are pretty cool. So.
Well, at my age and my health, I don't want to spend a lot of money on it.
Yeah. Okay. Well, everything is a compromise. There's no perfect telescope.
Not yet. Not yet. Okay.
Yeah, then actually another option we have is of course the 100 the diameter the ring is it only has 6 million ticks, so we can always increase that to 200 millimeter, so that will double the ticks to 12 million. So it's that's probably also result to the 0.1 arc-second resolution. Yeah. Yeah, that's it. Thank you so much.
Okay.
I'm done. Okay.
Thank you very much, Tong. Look forward to getting an update next year on how this turned out.
Yeah, I hope that the scope will be done by that time.
Yeah, well, we'll think good thoughts.
Okay.
And now we'll move on to David Davis and his talk about resizing Pyrex blanks in his kiln.
I have one more thing to say to Tong. On my presentation on Thursday night, I showed the Cal Poly telescope, and I forgot to give the credit that you made the mirror for that and gave it to the project. So thank you very much.
Thank you for mentioning that.
And it turns out to be a very good mirror. It's that and the secondary turns out to be pretty good.
Thank you, Tom. Thank you, Dan.
Are you waiting for me?
We're waiting for you. Yes, there you are.
Here I am. So, oh, see, I'm getting feedback. Didn't test that part.
Yeah, headphones or earbuds would cut that down, but if you don't have them, just go ahead.
I'm wearing earbuds, but it's the phone. It's the remote.
Oh, yeah. Okay.
Let me see if I can damp that off a little. Okay. I was going to share a couple of files with you, and I have on a machine, but I don't have them on the places that I can pull them up from. I need to get out to my drive, and I'm not finding that here anywhere. So, hang on. There, I took that thing out of the meeting. So, I'm David Davis. Let me click myself on here. Have I got anything going here?
Yeah, you're full screen.
but is my voice coming through?
Your voice sounds good.
All right, good. So I'm David Davis. This is my kiln room that I'm speaking to you from. I cobbled together a little bit of video so we could work on things. I'm still going to try and use the phone for remote. As I move away, I'm hoping we don't get the feedback and the echo. Except glasses. Okay, so I'm going to talk to you about resizing Pyrex blanks. But there's a couple of things I need to work on with you beforehand. And one of them has to do with the mold that I use to resize the blank. And that particular mold, and I will show you an example of it in a moment, got me to thinking about my existing molds that I typically use. I have one right behind me. And what I've discovered is that as you use the molds, here's the mold. As I use the molds, they heat, they desiccate, and then they absorb water back again. And they get to where they do that. They crumble.
Oh.
So they're good for 1 or 2 mirrors, but if you set them on the shelf for a year or two, they aren't worth anything. So when I got busy and started looking at resizing the blank, there was a gentleman down in Eugene that requested I do that. And I had a couple of 8-inch blanks here that I thought I would work with. And I put one in the kiln and did get it to slump down. One thing that I had wanted to show you that I'm not sure I can bring up. Wait a minute here. Maybe we can. Maybe I found the way to do it. So we get back to Zoom. Now can we share my desktop screen? If you've got a key for me here, let me know. Right here it is.
Okay.
Okay, so what we have here is called a tech note. And this comes from the company Bullseye Glass, bullseyeglass.com. And it's right here at the bottom of this screen. You can see the URL for it. And this particular one, they've got a whole list of them. This particular one is about heat and glass. And it runs all the way from about 1,000 degrees where you don't see much of anything going on, up to the range that I used. This is around where I slump glass into meniscus mirrors. And you can see you just start to get some movement in the glass. The corners are well rounded. It does a nice job. The layers will start to stick together nicely there. So if you are trying to fuse a piece of glass as well as slump it into a curve, if you get it up around 1350 to 1400 degrees, it'll stick together for you and then slump. You have to be careful, of course, because you do start to get some movement. So you can hang around at this area for an hour. Remember that as you're going up, I ramp up at 60 degrees an hour. So I hit 1300 and it'll be 2 hours later before I'm done and start to head down. That's why typically when I slump, I crash. Otherwise, I shut the kiln off and let it fall as fast as it can down to my target in order to start annealing and then take the tension out of it. This is the range I went into when I resized the blank. I'm up to 1650. I held it for an hour. I brought it back down. If we can bring this one back up, we can. Okay. Here we go. Get this back out of the road. Minimize this. They're all in the same place. Can you see that on your screen?
No.
All right. Stand by. New share. You have to be careful. Can you see it now?
Yes.
All right. This was my very first attempt at working Pyrex in a kiln. Pyrex says that the working temperature is 1800 degrees. 1800 degrees is where it pours like water. Don't go to 1800 degrees. This went in, ramped up quite slowly, got to the top. I held it for 2 hours, and you can see the result. When you get into the here, you can see that what you've got going is things start to come apart. Even though you've got brick in the kiln, and hopefully you're using your kiln on a relatively regular basis, as the brick desiccates and loses all of its water, and then the kiln cools and it sets for 2 or 3 days, it absorbs that water back. It won't lose that water quickly during the kiln process, otherwise during the ramp. And what you end up with is outgassing from the brick and from your mold, especially if you're using a cast mold like this. You'll start getting outgassing, which forces air and moisture up, and that's what causes these sorts of things to happen. You get little volcanoes, stuff runs. Above 1700 is a place that you probably do not need to go to resize your glass. This is probably as far as you want to go, right here. So with that little bit of word out of the road, I'm gonna turn this guy back on, Howard. And in just a minute, it'll ask you to let me back in.
Okay, admitted.
Thank you. Can you hear me?
Can hear you, but we just walked out of your the screen. That
Yeah, stand by. Stand by. Oh, we're in there. Oh. Well, and we're not getting our camera back up. Why aren't we getting our camera? I think it's because, oh, I know why it is. That should help. Oh, come on.
You're still sharing on your other computer.
Yes, I'm aware of that, and we're going to shut that down right now. Let me see. How do we shut it off? Okay, there we go. Now, there. Can you see it now?
Yeah, we just see the same. You just walked out of the screen with the phone. I think you might just have to shut your main computer off if you're going to share on your phone. I don't know that you can do both.
No, you can do
Same
both.
thing.
Well, I did it earlier in practice.
I can see him walking around.
Or you could see his phone?
Yep.
Oh, that's interesting.
Okay.
Scroll down in the list.
Oh, it's under a different name. It's under David Davis, but there's a second David Davis. Go pick up the other David Davis. There's bugs in the system. What can I say?
Yeah, it's true.
So, Tom, you can see this.
Yes, I can.
Wonderful. Have you up yet, Howard?
I'm looking for something on under my
I
settings.
believe that once you find the mobile video, Howard, you might be able to pin it so it becomes the primary thing that everyone sees.
I found it. You got to scroll all the way to the right.
If you go to gallery view, you'll be able to see his view moving around He's got a coffee cup. He's got, well, you can see a shop. There's the kiln.
I'll shut down the main computer and we'll just run the rest of them phone. We're going to leave on the main computer.
Yeah, well, you have to pin his video feed that's coming from the phone. When you do that, you're looking at his phone, filling the screen.
And if you log off your other computer, your voice will probably go away.
I got it now. Thank you, everyone. Okay. I have your video from your phone now.
But now I think we've lost his audio.
But we can't hear you.
No audio. You got to turn the audio back on your phone.
David, if you can hear any of us, but put 2 fingers up. No, I think he's messing with his phone. Okay, we have your video back now, David. Still can't hear you. No, we can't. Can anybody hear him?
No,
I can't.
No,
No, cannot hear.
Oh, dang it. And I don't think he can hear us.
If anybody's got his phone number, give him a call.
Yeah, I do not.
It sure looks cool, though.
Yeah, I agree. Yeah, see, this is.
I sent him a chat, but I don't think he picked it up.
Uh-oh.
Okay, he's logged on again.
I'm here. I hear
Okay,
you.
oh, you're back.
Okay, now we can hear you as well, but we couldn't get any audio from your phone.
Right. You did, though, see what I was showing you.
We did see what you're showing us, and it looked really interesting, but we couldn't hear a word you said.
Yeah, all right. Let me bring it over. It's never simple.
Yeah.
The gentleman that asked me to test had a 24-inch by 3-inch thick. What I had was a set of 8-inch blanks. Let me shut that back light off so we don't go sight through. I got both of these out of Goodwill, not out of the same Goodwill, and I got them a couple of years apart. This was somebody's Mirr, ended up in Goodwill. It had a little bit of coating left on it. So what I did was I made a mold like the one I showed you, which was just a kiln shelf that I put individual pieces around the outside to create a dam. And did you see the kiln shelf? No, I can tell.
Well, I'm sure, yeah, we did, but I don't know that we all know which one that is that you showed us.
And right now I'm not seeing anything.
He just walked out. He's going to bring it.
All right, so here's the kiln shelf. And what I did is I took pieces of brick, cut them to the size I wanted, cut a notch on one edge, and then they lay on the edge of the shelf like that. The pieces that I made, of course, I cut into pie shapes so they notched against each other tightly all the way around the outside. I then just used bricks against the back of them so they did not move and so that they also were held down in the kiln. The glass, if we can get back to, well, it's not there anymore. I'm not going to go dig for it. In the tech note at 1600 to 1700, you can see how the glass will start to flow. And if you read the notations there, it says the glass will begin to flow like molasses. So in order to figure that out, to watch that so it didn't get away, the kiln has two little tiny viewing holes cut into the side, two little tiny plugs. They're about 1 inch across. You can't see anything through that. So I opened up a large hole, a 3-inch hole in the middle of the lid. And then I moved my thermocouple to a hole in the plug that I made for the big hole in the top of the lid. So what I was able to do then was lift that plug out, look through a 3-inch hole, and get an idea of how quickly that glass was moving to the edge of the mold. And then I could drop that plug back in again and reseal my kiln and restore the heat process on the inside. I didn't set a time limit at the top. I just canceled once it had approached the edge of the mold. And then there was sufficient residual heat in the kiln to allow the kiln then to cascade down. And it worked. We ended up with this guy right here. That's Pyrex. It's fully annealed. Instead of 2 inches, it's 3/4 of an inch. Instead of 8 inches, it's 11 3/4 inches. So picked up almost a 12-inch blank. Yes, Dan, always better in the winter because there's no heat in this shop. So that was the process of slumping and bringing the glass into fruition. Now, I never saw the 24-inch glass. I don't know if it did something else with it. I don't know what happened to it. Richard Berry lost a bunch of mirrors in the fire. And he contacted me and said, do you think you could make those into mirror blanks for people? They're Pyrex. And I said, absolutely. Calculate the volume of the broken shard. And I think it would be easier to calculate the volume with a cylinder with water in it and see how much they displace. But on a standard mirror, it's very easy. Pi times radius squared by the thickness, and then divide it by pi again. Divide it by pi again, and you can figure out how far apart you can spread it, how far it will spread to what thickness. Actually, you divide it by the thickness first, and then do the square root. But anyway, lost my train of thought for just a moment. Okay, I'm back. So Richard, when he finally at last gets things cut up, will get a hold of me, and I will have a stack of burnt broken glass. I will be able to use this process then to turn those into modest size blanks, fully annealed Pyrex. And that in itself is a good thing too, I've learned from the process. But the second thing I learned from the process was the mold that I showed you, which is on the grinding machine behind me, and I can tilt down and you can see a long view of it. I have no way to zoom in on that. That's actually made of fire bricks. And around the edge here, there are 2 slots cut 3/4 of an inch deep. And then there is stainless steel wire in those slots, drawn up tight and twisted tight. What I'm doing right now is putting the curve in it. And unfortunately, you have to put the curve in just like you'd put the curve in anything else that you grind. So I have a gauge. That's across. It's not quite there yet, and it needs smooth. This is Tom, and I'm amazed. Tom and I think a lot alike because Tom asked Lisa a question that I was going to ask her later. Could we spin a epoxy mirror and use it as a positive to create the mold to slump on? I would like to make it out of the same stuff you make fire brick out of. But that's a long process because it takes a long time for that to lose all of its moisture. And that's the fire. The cement, and I use vermiculite, but I also use perlite. That soft concrete will work once or twice, but you end up throwing that mold away after you're done. I had, if we can bring it up, here we go. We're going to try and share one more picture here. Do you see the share?
Yes.
All right. This is a shot inside the 60 kiln. This was the old kiln that I built that I had in the shop for a long time. It began to rot out from underneath because of the heat cool cycle. And so I disassembled it, saved what I could, the rest went in the dump. What you see in front of you is Mel's 30-inch on the mold that Mel made. In this area here, as well as here, there's a crack. And that crack formed during the slumping process. And that crack also left an artifact in the slump surface. And so that's something Mel had to grind out. Also, the mold spalled, which meant that pieces of it, before the glass laid on it, got hot enough that they popped off. The outgassing blew it out. Think of like a volcano throwing out rocks. Same sort of thing. The heat drove it apart. Not significantly, but enough of them that he had dimples on there that he also had to grind through. And he did a job of it, I might add. That's what I'd like to get away from. That's why I wanted to work with Lisa about getting a mold from her that I had sent her back at an earlier time so that spin epoxy on it and see how it works. Tom, you want to add anything to this?
No, I've actually been exchanging emails with Lisa just to kind of describe the process. So yeah, and I had the same problem with an artifact being cast into my glass. And I'm a little discouraged that you're saying that I can only get two uses out of the form because I was planning on reusing mine again. But I agree, it turns into styrofoam after a couple of uses. So to be able to quickly redo it, I think is the key. And so, if we can spin cast to a particular curvature and then just make a new vermiculite cement mixture, as needed, I think that's definitely the way to go.
Yeah, that's the issue. Is we're breaking the cement bond that we're using to create the concrete by the heat. And it'll hold for a while, but yeah. I'd like to get rid of the artifacts. So that particular mold behind me is being created to slump two 20-inch F35s. And I have a 20-inch glass of my own leaning down here against the front, and I will slump that on the mold first to make sure it doesn't do something strange. The two pieces of glass I have are beautiful pieces of glass, and I certainly don't want to screw them up. So kind of strange, torn apart, a little bit of Charlie Chaplin, but hey, that was my presentation. And I still brought it in pretty quick.
Yeah, you did great. Thank you very much. Oh, heck, no, see, I had a senior moment. I was going to ask you a question and now I forgot.
I'm glad I'm not the only one.
On the photo you have of Mel's 30-inch.
Yes.
Sitting on a slumping mold, did you use the same slumping mold for both 30-inch mirrors?
Yes, but I didn't move it.
Okay,
the second mirror actually came out better than the first.
Oh.
Because the first mirror allowed all the air to go on. And then before I put the second one on, I put a dusting of kiln brick powder in the holes and brushed it off with a little paintbrush. It's the same thing that Tom's when he builds his molds to cover in the holes where the perlite comes up and the concrete's a little low.
And you did proof the mold the first time, right? So before the glass went on, you actually did a run.
Yes. And in fact, let me see. We'll tempt fate here. I've been known to, and this was something I wanted to show you also. This is the ultimate kiln. This is called a sand bed kiln. And this is what I tried to do initially. This is in a commercial glass place back in Illinois. This is from a video on YouTube called Hands-On History Bulletproof Glass. And he goes through creating bulletproof glass, but there's about a 3-4 minute segment in the middle where they work inside this kiln, creating the shape they need in the sand, and then they run the kiln to fuse the glass and also bend it into shape. Andrew already tried this also. The bed in his kiln was sand. It was too coarse a sand to be able to rake smooth and beat down that way. There is another one here. And so we'll show this one now. Oh, quit it. I'm starting to get the hang of this. I wish the camera would have worked. You can see what they're making here are Art Deco rounded windows. Can you see that one?
Yes.
Okay, so there are 2 rails on the side of the mold, and that's what the glass lays on, and that's what preserves the edge. When I attempted to make a slump for Mel initially, we used a sand mold in a ring, but I didn't have broad surface for the glass. I laid the glass on the edge of a band of metal. And we also didn't beat the glass in or the sand in like these folks do. These folks actually take a compactor in there and beat that glass down solid and then scrape their shapes into it. Sand bed kiln. It'd be nice to have. As long as we're going and nobody says, knock it off.
No, if you got more, go for it.
So this is an example of the spall marks that it left in the first 30-inch. Each one of those little things here is a little divot where the mold spalled and then glass laid down on it after the fact, put a little divot in the glass. Those all had to be cleaned out. So it was extra grinding for him. This one, shows the cracks. So there is a crack right here. Pardon me. There's a crack just below the edge of the thing here you can't see. But you can see this crack actually migrates in about 6 inches. And so then you've got, here's more spall marks right here. That's why I didn't move the mold after I slumped the first 30. I just filled the holes, swept them in smooth, and then laid the next piece of glass on top. Got no spalling the second time around. No spall, well, one or two spalls the first time around, but not like I did after the first piece of glass. Tom asked, did you test it? And if you always test it, you take it up to at least 1,000 degrees to see if it's going to pop or crack or spall badly or whatever. And it survived. It did a good job.
In my case, I tested it and it worked great. And then when I slumped, I got a spall right on the edge. That was so deep that it was just not worth taking out, but it was very frustrating.
Yeah, I've got Tong Liu in the background.
Yeah, I'm typing him a message.
Okay.
Just one comment on your tech note there. With those temperatures, whoever is tempted to do this sort of thing, those temperatures are highly dependent on the particular type of glass. So like, for example, I was slumping at 650 centigrade, not the 700 plus that seems to be indicated on that. And I guess that's the difference between Pyrex and plate.
Yes. Yes, that's exactly it. Plate has a much lower number in it. Pyrex is above that. This is an example of one of my mold castings. And I cannot remember which piece of glass I've cast off of this, but I use regular food grade plastic because it lays in much tighter. And so, and then it just looks like cement, but that's actually 1 part rapid set grout and 5 parts vermiculite mixed and poured in. So I use the rapid set because it's done in an hour, and then I can see if I've screwed up and I can get another shot at it or whatever. Any other questions?
Well, Dave, I will have maybe 100, 120 pounds of Pyrex for you.
Oh, wow.
Well, there's a 20-inch full thickness mirror, 2 or 3 12-inch full thickness mirrors, and a 10-inch full thickness mirror. These were all pieces of glass I got before we got into making thin mirrors.
Yeah. Yeah. It's a horrible loss, but if we can salvage most of it, that's a good thing.
Yeah, you may want to sandblast them because there is external material. In some cases, it looks like a little bit of aluminum might have melted into the glass, because when telescopes melt down and they have aluminum tubes, the molten aluminum flows onto the Pyrex, and then the Pyrex slumps.
Yeah.
You should be prepared to sandblast it or something. In other cases, the surface simply went wrinkly.
Yeah, this particular thing that I slumped, it was somebody's mirror, and it actually had a coating on it, and I just heated it up and melted it. I don't know if you can see, I was going to show this detail. The footprint, try and get the light just right. Yeah, you can see it. The footprint is between my fingers. That's the original disc. That's the base of it.
Mm-hmm.
And so all it did was get hot and just flow out until it filled the dam all the way around. It's not the best of videos. It's close.
Yeah, I mean, one possibility is you might want to, I hate to suggest this, but take a sledgehammer and break it up into about 2-inch size pieces, little cubes, and then slump them all together.
On your material?
Yeah.
Yeah, I actually have access to a saw that will cut most of that.
Okay, well, I'll send
and
you.
So I can slice it into pieces and lay the pieces down and mix and match them in to fill.
I think that might be the best. I'll send you photographs as we begin to collect it together.
Okay. Sounds like we're done, Howard. I don't hear anybody
Any more
else.
questions? Yes. I was just going to say, I think we may be. Well, that's really fascinating stuff, David. And I can think of probably a lot of people here right now who would probably be honored to get one of those blanks that come from the glass that were lost in the fire at Richard's place. That'd be quite an item.
They'll be available ultimately.
Yeah.
David, do you think there'd be any issue with non-uniformity, with multiple pieces of feed glass and different effects from the fire and everything else? Will you have to stir it, or?
I don't think so. I would probably, like the 20-inch, I would probably use as much of that as could just by itself. Then I know I've got the same mix, the same cast. The remaining pieces would probably be best used by crushing them down and then mixing them well and then putting them together, creating a mix, basically. Then it would be homogeneous enough that I don't think you'd have any issues with it.
Yeah, and another thing that we have, the C14 and the C11, I doubt they use Pyrex in those, but that's another 20 pounds of material, roughly.
Yeah, we should be able to do a diffraction test on that, I think, and figure out whether it's Pyrex or something else.
Yeah, well, it's better to send it to you than send it to a dump.
I've always been honored to be a dump.
Well, no, you're better than a dump.
You're better than a dump. This is a chance for something to come back and have a new life. I think it's a good idea.
Yeah.
I think that's an excellent idea. And Dean Kettleson has a stack of Borafloat in the back of his lot here in Tucson. And he bought a whole sheet and cut out some mirrors, and there's some leftover cut out glass there. So.
Well, you know, I'm always into road trips. If he wants to get rid of it, I can drive down and go to the Grand Canyon again.
Well, maybe next year we'll have a Grand Canyon.
Yeah, maybe.
Yeah, okay. Well, this is awesome. Thank you again, everyone. I really enjoyed all the presentations tonight. We had a really interesting mix, and it's always a treat to either see or be in your kiln shop there, David. It's quite the place.
That's very polite of you.
Well, no, it is quite the place. You just look at the wonderful things that Mel is doing with those 30-inchers. Holy cow!
Yeah,
pretty incredible.
The kiln that did those is gone, unfortunately, and I don't have any place to set it up in.
Yeah.
So it's yeah.
Yeah. Okay. Well, we'll leave that for tonight.
I have one more question.
Oh, one more question. Go ahead.
I grew up in fire brick country, and I'm wondering if you've ever thought about trying fire clay as a mold.
Yes. Yes. Have played with that. The problem is the drying time and the drying consistency. And I don't have a good handle on that yet. The molds that I made that way cracked on me. Every one of them did. That's why I eventually went to the castings. But I'm always willing to learn. If you've got some secrets, I'd love to hear them.
Well, I was too young to know what they were doing in the brickyards, but the little town I grew up in was famous for its fire brick.
Yeah.
Okay. Well, I think we'll wrap it there.
Good night.
And oh, somebody else?
I was just saying good night.
Ah, okay. All right, good night. And just a reminder for tomorrow, we'll again start at 5 o'clock Pacific time. Mel will start off with a update on his 25-inch telescope. And then Russ, Dan, and Dave Rowe will be a small panel on a robotic speckle telescope that they've all contributed to. And after a short break, we'll hear from Ed Allen again about his updated clutch system from his 24-inch Elvira telescope. And having used his original clutch system, it's hard to imagine how he was able to improve it because that worked so well. But he's going to talk to us about that. And then we'll have a video called Next Generation Telescope Program at TNO. And this is a group in the Netherlands. And I was given a heads up from Don Peckham on them, and they agreed to participate this year, and we'll watch their video, which I got today. So hopefully that'll be something that I haven't been able to watch it yet, but hopefully that'll be a really good addition to our program, and that'll be the end of our workshop. So again, thank you all again, and have a great rest of your evening, and you'll see y'all here tomorrow.
Are we going to have a barbecue tomorrow?
Thank you.
I think we should all have a cold beer ready at the end that we can all share together.
Okay,
At the
that's
very
the
least.
best we can do. Okay,
I think
that
it's the
sounds
best way.
good.
If you want to have barbecue some chicken, you're on your own.
Okay, great.
Thank you, Howard. Thank
Yes,
You're very
thanks,
welcome.
Howard.
everyone.
Howard.
Y'all have a great night.
You
Thanks,
too.
Howard.